Alrighty, let's move on to section 5.5. And before we get into what section 5.5 is, I want you to go ahead and pause the video and really quickly go ahead and fill in all of the identities on this first page. Okay, see if you remember it from the last time we've done some homework. Hopefully these are becoming quicker and quicker for you to recall. Okay, so go ahead and pause the video. Once you get it filled out, play it again, make sure you got them all correct, and then we'll jump into 5.5. Okay? Okay, let's see how you did. Reciprocal identities, we know that cotangent and tangent are reciprocals. We know that secant and cosine, and we know that cosecant and sine are reciprocals. So hopefully those were all quick. Our Pythagorean identities, we have you sin, you confess you're one with God, right? Sine squared plus cosine squared equals 1. 1 plus tangent squared theta equals secant squared theta. 1 tan second. Just give me 1 tan second, right? And then 1 cocos. 1 plus cotangent squared equals cosecant squared. So hopefully those are becoming more and more familiar with you. We also need to make sure we keep in mind our negative identities. Hopefully you noticed on some of the proofs from section 5.2 of 5.3 and 5.4, we used these negative identities, which basically says that cosine and cosecant, the cosine value is the same whether we use the negative angle or we use the positive angle, right? Cosine and secant stays the same, but sine, tangent, and their inverses, the sign changes, right? We go from a negative angle to a negative value when we switch to a positive angle. And then our quotient identities, again, hopefully these are ones that are really second nature to you at this point. Tangent is the ratio of sine to cosine. Cotangent is the ratio of cosine to sine. Okay, so hopefully this is a nice quick reference page where you're being more and more familiar with these identities. Okay, what we're going to talk about in section 5.5 is we're going to talk about double angle identities. And I'm going to write it big on the top of the page. We'll just call it formulas. Double angle formulas. That way when you're flipping through your notes, if you're looking for those double angles, it will be easy to find because you'll have it nice and written big at the top of the page. Okay, so what we're going to do is I'm going to verify that each formula, kind of show you where it comes from, and then we're going to do a little example of each one. Okay, and then we'll go into how we can use these formulas to do other proofs and other types of problems. So the first one that we want to come up with is this formula. Now these would be good formulas to write down on a note card or on a page so that they're easy and quick to reference versus having to flip through all the pages of 5.5. Okay, all right, so this angle says that cosine of 2 times angle A is the same thing as cosine squared minus sine squared A. Okay, so we're going to use this cosine identity, the sum of cosines. Remember this was our cab-sab, right? We're going to use that formula to try and rewrite this one. This one is actually may have been one that I had you prove on a previous worksheet. So hopefully this isn't too foreign. Okay, when we have 2 times A, that basically means we have 2 copies of A. So we could rewrite this as cosine of A plus A, right? A plus A is the same as 2A. But writing it like this allows me to have 2 separate angles like we had previously in our sum of cosine formulas, right? So now that I have 2 separate angles, I can say this is my first angle and this is my second angle, and I can plug it into this formula that we're already familiar with, right? Which says we do cosine of the first angle, so cosine A, times cosine of the second angle, which in this case also happens to be A, minus sine of the first angle, which is A, and sine of the second angle, which here is also A, right? And then we can rewrite this, right? Because if we have cosine of A times cosine of A, I have 2 copies, right, being multiplied together, and we can represent that with a squared. So this is the same thing as saying cosine squared A, and then the same thing is true with my sine terms. Sine A times sine A, I can rewrite that as sine squared A, okay? And that's exactly what we were trying to prove, is that cosine of 2A, what we started with over here on the left, is equal to cosine squared A minus sine squared A. So we have it proved. Yay! So now that we have it proved, we can go ahead and utilize it. So let me show you an example just to kind of verify that we believe this is true, right? So if I wanted to simplify cosine of 60 degrees, right? So notice our formula says that we have 2 times some known angle, A. 2 times some known angle A. So what I'm looking for is I am saying I can rewrite 60 as 2 times some angle, right? 60 is the same thing as 2 times some angle A. So if I solve this, right, then A would have to be what? If I solve this, I'm trying to figure out what angle when I multiply it by 2 gives me 60. Well, I would just divide both sides by 2, which would tell me that A would have to be 30. Right? So in other words, I can rewrite this as the cosine of 2 times 30 degrees, right? You all agree that 60 degrees is the same as 2 times 30 degrees, right? But I'm writing it in this way so that I can use this formula that we just came up with, right? Which says cosine of 2 times an angle. So here my angle is A. We can rewrite that. Our formula tells us to do cosine of A, cosine squared of A, and our A is 30 degrees, minus sine squared of A, which is 30 degrees. Okay? And then we can look back at our chart or our unit circle, right, to find these values. So I'm going to go ahead and just tell you what they are so I don't have to keep sticking the chart in here. So if I look for cosine of 30 degrees, cosine of 30 degrees is the square root of 3 over 2, right? But notice this isn't just cosine of 30 degrees, it's cosine squared of 30 degrees, which means we're going to square that value. So I'm going to go ahead and put a square around it. And then the same thing with sine squared of 30 degrees. If I look up the sine value of 30 degrees, it's 1/2. But because it's sine squared, we're going to go ahead and square it, right? So let's go ahead and square these values. On top, when I square root, that cancels, so I'll just be left with 3. On bottom, 2 squared is 4. Minus, over here, when I square the 1, I get 1. When I square the 2, I get 4. So 3/4 minus 1/4 gives me 2/4, and that is 1/2. Okay, so we're really just verifying that we believe that this formula works. So what we did is we used cosine of 2 times a 30-degree angle to show that this is equal to 1/2. Now notice, if you were to look up cosine of 60 degrees on our chart, if we go down to 60 degrees and we look at the cosine value, it is in fact 1/2. Okay. So this gives us a new way of finding angle values. Now, this may seem really insignificant, like why would we want to rewrite 60 degrees into 2 times 30 when we could just look up 60? The reason that we have these double angle formulas is we're going to need them whenever we go into creating half angle formulas, right? So if I wanted to find cosine of 15 degrees, we could figure out, oh, well, that's half of 30 degrees. So that's where we're headed. But we can't get to those formulas without first coming up with a double angle formula. Okay? So again, proving that it's true and then verifying with an example that it is in fact a valid way of finding these trig function values. Okay? All right. Now, an important note that some people make, or a mistake that a lot of people make when they're doing proofs in this section, is they assume that cosine of 2a is the same as 2 times the cosine of a, and this is not true. Okay? This means all I'm doing is rewriting the angle that I have as its half value times 2. Okay? It does not mean that I'm taking a whole different one. In other words, I can't say that cosine of 60 is the same thing as 2 times cosine of 30, right? Because you agree that A here would have to be 30 in order for this to be 60. Well, cosine of 60 is 1/2, but cosine of 30 is square root of 3 over 2. And if I multiply that by 2, that gives me the square root of 3. So this is not a true statement. Okay, so make sure you're not claiming this when you do proofs. Okay, this is a big time no-no. So if you need to highlight that or do whatever you need to do so that you don't make that assumption, it is a false accusation. Okay? All right, so we have now this formula that cosine of 2a is equal to cosine squared a and sine squared a. But we have a Pythagorean theorem that says you sin, you confess you're one with God, right? That would allow us to replace either of these with something else. So we actually can come up with two additional formulas for cosine of 2a. So let me show you those. So the first one is cosine of 2a is equal to 1 minus 2 sine squared a. So we're going to go ahead and start with cosine of 2a, okay? And we're going to use the formula that we just proved. So the formula that we just proved was this one. Cosine of 2a, this is the one we proved at the top of the page, is equal to cosine squared a minus sine squared a. So I'm just going to go ahead and start with that. Cosine squared a minus sine squared a, okay? And notice what we're wanting to work towards is that this can be rewritten as 1 minus 2 sine squared a. So I want to end up with only sine squared terms. I don't want any cosines over here, right? So I'm going to try to figure out how to eliminate this cosine. I want to eliminate this cosine or rewrite it as something else. So I can use our Pythagorean identity, right, that says you sin, you confess you're one with God. They have these two terms written backwards, but same idea. Cosine squared plus sine squared equals 1, and I can solve it for cosine a, right? If I solve this for cosine squared a, what I would get is cosine squared a is equal to the 1 that's over there on the right-hand side, and then all I would have to do is move this sine squared a term to the other side. And the way that I move that sine squared a term to the other side is by subtracting it, right? So what that tells me is that cosine squared a can be rewritten as 1 minus sine squared a. So I'm just going to replace this cosine squared a with what I found it to equal. So now we have 1 minus sine squared a minus sine squared a. And I just put parentheses around it so you can see I'm substituting this in for that. Okay? But I don't really need the parentheses there because there's nothing being done to that cosine squared a, so that means there's nothing being done to this quantity. So if I drop the parentheses, I end up with 1 minus sine squared a minus sine squared a. And you can tell now that I have two like terms, right? I have a negative sine squared a and I have another negative sine squared a. And those are just like terms. So negative 1 and negative 1 gives me negative 2. So I can write this as 1 minus 2 sine squared a. And that's exactly what I was working towards here, right? So I have proven that cosine of 2a is equal to 1 minus 2 sine squared a. Okay? So this is something I would look for you to be able to do on a test. If I tell you to prove this formula using these two identities, I would assume that you could, in fact, do that. Okay? All right, so again, let's verify it. Cosine of 60, we've already done this one, right? That's the same example we did before. So we already know that this should equal 1/2. But I want to go ahead and verify that it equals 1/2 using this new formula that we've come up with. Okay, so our new formula says that if this is the same thing as 2 times an angle, which just like our last example, we know that we can write 60 as 2 times 30. So this is the same thing as cosine of 2 times 30 degrees. So again, 30 degrees is our A. Okay. So here's our double angle formula. And the one that we just proved is that it's the same thing as 1 minus 2 sine squared A. So we're going to do 1 minus 2 sine squared A, and our A in this case is 30 degrees. Okay. So let's go ahead and put in those values. So I have 1 minus 2. Now sine squared of 30. First I look up sine of 30. Sine of 30 excuse me, is 1/2. But it's a sine squared, so we're squaring that value. Okay, and then order of operation tells us that we want to do the exponent before multiplication. So we're going to square the 1/2. So I have 1 minus 2 times 1/4, right? And now I can do that multiplication. 2 times 1/4, or 1/4 of 2, right? I can reduce by 2 on top and bottom, and I end up with a negative 1/2. If you're not good with fractions, you can always use the fraction button on your calculator. And then 1 minus 1/2 is, in fact, 1/2. Good. So we just verified that we know cosine of 60, even when we put it through our new formula, does give us the correct value of 1/2. Okay. All right. So now we have two formulas so far for cosine of 2a. We have cosine squared a minus sine squared a, and now we have 1 minus 2 sine squared a. Now, remember, the way that we got the second one is we took that Pythagorean identity and we replaced the cosine squared a with a sine value, right? We could do this exact same process, but instead of replacing the cosine squared a, we could replace the sine squared a. So that's what we're going to do on the next page. So that's going to give us a new cosine 2a formula, but this time one that only has cosines instead of sines. Okay? All right, so let's look at the next page. The formula we're trying to prove is this one. Cosine of 2a is equal to 2 cosine a, or cosine squared a minus 1. Okay, and we're going to start off with our original formula that we proved at the very, very beginning. And then we're going to use our Pythagorean identity to get rid of our sine term. Okay, so we're going to go ahead and write, oops, I didn't mean to turn my paper, sorry. We're going to start with this first one, that we know that cosine of 2a is equal to cosine squared a minus sine squared a. The first one we proved today. Okay. Now, we want to end up with just cosine terms. So now the sine squared a is what I want to get rid of, right? So I'm going to use this Pythagorean identity that we have written here, and I'm going to solve it for sine squared a so that I can replace this, right? So to get sine squared a by itself, sine squared a, I already have the 1 on the other side, right? But I would need to move this cosine squared a to the other side by subtracting. So minus cosine squared a. So I'm going to take the sine squared a, which I know to be 1 minus cosine squared a, and replace it in my formula here. So this is cosine squared a minus, if I replace the sine squared a, I'm going to put in a 1 minus cosine squared a, okay? Just plugging in for sine squared a what I know it's equal to. And here it is important that you use parentheses, okay? If you didn't use parentheses on the other one, meh, it kind of worked out. But this one, it does matter because we're replacing one term with two terms. And since that one term is being subtracted, we have to ensure that that subtraction will get distributed to both of my new terms, okay? So that's what I'm going to do in the next step, is go ahead and distribute that negative sign. So now I have cosine squared a minus 1 plus cosine squared a. And now I have 2 cosine squared a terms, right? So I can add those together like terms. So that becomes 2 cosine squared a minus 1. Okay? And that is, in fact, what I was trying to prove cosine of 2a equals. So here we have proven what we wanted. And now we just want to go ahead and verify it, okay? Just like the other ones, it's always good to do an example with real numbers to make sure we got the correct value. So again, we already know that cosine of 60 is equal to 1/2, but let's go ahead and verify it with this new formula. So the first thing I want to do is I want to write it as a double angle. Instead of cosine 60, I'm going to go ahead and write this as the same thing as cosine of 2 times 30 degrees, where our angle A would be 30, right? 30 doubled gives me the 60. And so we're just going to go ahead and verify this new formula we came up with that says that cosine of 2 times 30 degrees is the same as 2 cosine squared A, which our A is 30 degrees, minus 1. Okay. Now, if we look up cosine squared, or sorry, if we look up cosine 30 on our chart, we know that cosine is the square root of 3 over 2. Cosine 30 here is being squared though. So we're squaring that. Then we're going to multiply it by 2 and subtract 1. Okay. So when I square this fraction, because I do the exponent before multiplication, so don't cancel the 2's here, right? We have to do the exponent first. So square the square root of 3 just becomes 3. And we square the 2, which becomes 4. We're going to multiply that by 2 and subtract 1. Okay? And I'm running out of room, so I'm going to work this way. So here, now I can go ahead and cancel the 2 and the 4. 2 goes into 4 2 times. So that leaves me with 3 halves minus 1, right? And 3 halves, that's 1.5, right? So 1.5 minus 1 does, in fact, leave me with a half. Okay, so we get the same thing with our new formula. Yay! Okay, so what we have determined now is that we have 3 different formulas. These are the 3 formulas, and I encourage you to write all these formulas on a note card or on a piece of paper that you can kind of keep with this section. So the first one that we proved at the beginning of class was that cosine squared A minus sine squared A gave us that double angle value. Then we substituted to get rid of the cosine squared term, and we showed that cosine of 2a can also be written as 1 minus 2 sine squared a, right? And then we also showed that we could get rid of the sine squared a term, and we could rewrite this double angle formula as 2 cosine squared a minus 1. So it's good that we have 3 different options here, because depending on what our problem is asking us to do, or our exercise is asking us to verify or prove, it may be easier to use one more than the other. Okay. All right. So now we have those written down. Now what we want to do is we want to come up with a double angle formula for sine. So now we're switching gears. Sine of 2a, we want to show that that equals 2 sine a cosine a. Okay, and this one's actually a little bit easier to prove than the other one. So we're going to start off with our sine formula. Remember, this was the so cool, ABBA so cool formula that says if we have a sum of angles, our sum formula would be sine of the first angle cosine of the second plus sine of the second cosine of the first. Okay, so we're going to use that to rewrite sine of 2a. So the first thing I need to do is rewrite 2a as a sum of 2 angles. So 2a means that I have 2 a's, right? Which I can write as sine of a plus a. And now that I have it written as an addition, I can just plug this first angle a and the second angle a into my formula here. Okay, my formula says to do sine of the first angle, so sine a, times cosine of the second angle, so cosine, my second angle is a, plus sine of the second angle, so my second angle is a, so sine a, times cosine of the first angle, so cosine a. And if you notice here, because both of my angles are the same thing, they're a, what I end up with is sine a, cosine a, sine a, cosine a. So these two are actually like terms, right? And when I have like terms, I can add them together. So this is the same thing as saying 2 sine a, cosine a. And that's exactly what I was proving for this formula. So we have in fact proven it. Yay! Okay, so now we're going to use an actual angle value to verify that this works. So if we look up 60 degrees on our unit circle and we look for the sine value, it should be square root of 3 over 2. This should equal square root of 3 over 2. But we want to go ahead and verify it with this new formula that we came up with. So first thing is, notice my new formula has a double angle in here. We need to write it as 2 times some angle value. So the angle value that we would have to multiply by 2 in order to get 60, again, would be 30. So I'm going to write this as sine of 2 times 30 degrees so that 30 degrees will be my A value here, or my double angle, okay? All right, and now let's plug it into our formula that says this should equal 2 times sine A, my A is 30 degrees, times cosine A, so cosine 30 degrees, right? So now we can go ahead and plug in these values. So 2 times sine of 30 degrees is 1/2. And cosine of 30 degrees is square root of 3/2. So notice when we go to simplify this, 2 times 1/2, my 2's will just cancel, and that's just 1, right? So 1 times square root of 3/2 is square root of 3/2, which is in fact what sine of 60 equals. So, yay, it works. Okay. All right. So now we have our sine formula, and we only have one sine formula. So yay for not having to go through this a million times, right? Because the reason that we were able to come up with 3 cosine formulas is because we had cosine squared, sine squared. So we could use the Pythagorean identity to come up with alternate versions. But here, notice, we just have sine and cosine to the first power. So there's not a lot of substituting we can do to make this look different, right? Okay, so now we have our 3 cosine angles that we've come up with, and now we have a double angle formula for sine. So the last formula we want to come up with is a double angle formula for tangent. Okay, so if we look on the top of the next page, we want to come up with a formula, or specifically with this formula, that says that tangent of 2A is equal to 2 tangent A over 1 minus tangent squared A. And we're going to solve this one the same way we did the sine and the cosine ones, right? The easiest way to rewrite this as something, if it's 2 times A, is to just write it as A plus A, right? And then once we have it written as an addition, then we can plug it into the tangent formula we already have for addition of angles, okay? So we're going to go ahead and write this as tangent of A plus A. Now that we have it written as A plus A, this is my first angle, this is my second angle. So no matter where it says to plug in an A or a B, I'm basically plugging in an A. So when I plug these 2 A's into my tangent formula up here, my sum formula, it says to do tangent of the first angle plus tangent of the second angle. So tangent of my first angle, A, plus tangent of my second angle, which is also A, all over 1 minus tangent of my first angle times tangent of my second. So tangent of my first angle, A, times tangent of my second angle, which is also A. And now I can just simplify the way it's written. On top, I have like terms. Tangent A plus tangent A, that means I have 2 copies. So I can write this as 2 tangent A. And on bottom, the simplifying that I can do is on the second term, tangent A times tangent A. I could write that as squared, right? Because I have repeated multiplication. So I could write this as tangent squared A. And that is, in fact, what I was trying to prove for this formula. So we have proven that. Ha-ha! Right? And now we just want to verify it with an example. So our example that we're going to use is tangent 60, and I'm going to move it up a little bit because it looks like when I worked it out it was kind of squinched. So I'm going to go ahead and move this example up here. I'm going to say that tangent of 60 degrees, we know we can rewrite that as 2 times 30. So that's the same thing as tangent of 2 times 30 degrees. 30 degrees will be our A. So now the formula we just came up with here, right, that we want to verify, is that this is the same as 2 times tangent A. So 2 times tangent A, which A in our case is 30 degrees, all over 1 minus tangent squared A, or tangent squared 30. Okay? And then I just want to go ahead and plug in my values. So 2 times tangent of 30. If we look up the tangent value for 30 degrees on our unit circle, it's 1 over the square root of 3. Okay, and I'm not going to worry about rationalizing the denominator until I get down to having a nice pretty fraction. Okay, so I'm going to leave it like that. Then on bottom, I have 1 minus tangent of 30 degrees squared, right? We already know that tangent of 30 degrees is 1 over the square root of 3. But here on bottom, it's going to be squared. Okay, so I'm going to do a little simplifying here. So on top, 2 times 1 over the square root of 3, I can think of this as 2 over 1, right? And just multiply straight across. So that would give me 2 over the square root of 3. On bottom, I'm going to go ahead and square out this second fraction. So I get 1 minus, square the 1 on top, I get 1. Square the square root, I'm left with 3. Okay, so I'm going to come down here. So on top, I have 2 over the square root of 3. On bottom, 1 minus 1/3 is 2/3. Okay, and then remember, when I have a fraction over a fraction, that means I'm dividing fractions. And the way that we divide fractions is we flip and multiply by the reciprocal of the fraction that we are dividing by, right? So here I'm going to multiply by 3 over 2. And when I do that, I should be able to now cancel these 2's. So I end up with 3 over the square root of 3. And then this textbook requires us to rationalize our denominator. So now to get the square root of 3 out of the denominator, I'm going to go ahead and just multiply on top and bottom by the square root of 3 over 3. And I'm just going to make a note. Rationalize denominator. Okay. So what we end up with is 3 times the square root of 3 over square root of 3 times square root of 3, square root of 9, right, which is just 3. And then we can cancel our 3's. So we end up with square root of 3. And if you look up what the tangent of 60 degrees is, it is in fact the square root of 3. So we have verified it with a specific angle value. Okay. Okay, so on your little note card or on your little piece of paper, we should now have five new double angle formulas, okay? So I would suggest that you write them down on a piece of paper so that you have them easy to reference when you do this homework. So we have the 3 cosine of 2a angle formulas. We have the sine of a double angle, and now we have the tangent of a double angle. So as we go through the rest of the problems in this section, I'm going to reference these that we've proven instead of flipping back through all the pages that we've gone through, okay? So I encourage you to write those down so that you have those super handy for when you are solving problems. So let's go ahead and look at some. So this says, given that sine theta is 8 over 17 and cosine theta is less than 0, find the values for these 3. Okay, now these are the formulas we just came up with. So we need to figure out what would be the best formula to use for these that we just came up with, and do we have enough information to solve them? So without even thinking about what was given to us, if I want to find sine of 2 theta, that's my sine formula, right? That's this one right here. We know that sine of 2a, or in this case it's 2 theta, right? We know that's going to be equal to 2 times sine theta cosine theta. So notice here my theta is the a, right? Same formula, they're just using theta instead of a. So this should be 2 sine theta cosine theta. That's the formula that I need to plug in for so I can find that sine value. So let's look at what was given. What was given was the sine value of theta. So I can go ahead and plug that in, 2 times 8 over 17, but I still need to know the cosine value. And the only thing that I was given in regards to the cosine value is that it's less than 0, so we know it's negative. So we're going to have to do a little calculating in order to be able to finish this problem. So let's think about what we know. If I look at just these 2 items that were given to me, sine is 8 over 17. That means my sine value is positive, right? So sine relates to the y. So notice sine is positive here, sine is positive here, and sine is positive here, right? Above the x-axis is where I get positive sine values. And then it says that cosine is less than 0. So the quadrants where cosine is less than 0, cosine relates to my x, right? And my x's are negative on this side of the y-axis. So over here we know that cosine is negative, and down here we know that cosine is negative. So if we have a positive sine value and our cosine has to be negative, the only place that that can happen is right here in quadrant 2. So what was given allows me to figure out that my theta has to be over here in quadrant 2, right? This is my theta, right? Okay, so, or well, from here to here is my theta technically. But now that we have that, we should be able to label this triangle and be able to find all the values of the length so that we can find the cosine. So we know that sine is 8 over 17. So sine is opposite over hypotenuse. So that means the opposite value is 8. The hypotenuse value is 17. So we should be able to find this adjacent side just by using the Pythagorean theorem, right? That says that x squared plus my y squared, which in this case is 8 squared, is equal to my hypotenuse, which is 17 squared. And now we just have to solve that to figure out our x value, okay? So this gives us x squared plus 64 is equal to 289. And then we move our 64 to the other side by subtracting. So I get x squared is equal to 225. And then to get rid of the square, I have to take the square root. So when I take the square root of x squared, remember I have to do plus or minus the square root of 225. So that means that x is either going to be a positive or a negative 15, right? So again, let's think about what quadrant we're in. We're up here in quadrant 2. Notice our x values are going to be in the negative. So we're going to take the negative. So negative 15 is going to be that length, okay? All right, so now that we have our triangle completely labeled, now we should be able to figure out the cosine value. So remember, cosine is adjacent over hypotenuse. Now we know our adjacent value is negative 15 over our hypotenuse value, which is 17. And all we have to do is multiply those three numbers together, which gives me negative 240 over 289. Now again, on problems like this, I would suggest using your calculator, the fraction button, because once you plug it in using the fraction button, it will go ahead and reduce it for you. So if you have a calculator that looks like this, it's the N over D button. If you have a calculator that looks like this one, it's going to be this A, B over C button. Okay, let me see if I can get that a little bit better in focus. Okay, so if I want to check if negative 240 over 289 reduces, with this calculator I would do negative 240 and then touch my fraction button, that A, B over C button, and put it over 289 and hit enter. And notice it gave me the exact same thing. And that's also what will happen if I do it on this calculator. If it gives me the exact same thing, that means that it's not reducible. Okay, so that is my answer for this one. So I'm just going to leave it like that. Okay. All right, now I want to use my cosine double angle formula to calculate this one. Now, you have choices here, right? Because if we look back, remember we had 3 different double angle formulas for cosine. So I want to think about which one is the smartest one to use in this case, okay? This one requires us to know cosine and sine. This one requires us only to know sine, and this one requires us only to know cosine. So looking at my problem, I want to choose the one that's going to require me to use the least amount of values that I had to figure out. That way, in case I made an error, it's less place for me to make an error. So in other words, for this problem, the value that was given was a sign value. We know without a shadow of a doubt that the sign value is 8/17 because that was given, right? I didn't have to solve for that. That was given. So if I can use a formula that just uses sign, that's going to be my best bet because I know I didn't screw up this sign value. It was already given to me. So if I look at my three formulas, there's one that only requires a sign, the second one, right? Cosine of 2 times an angle is the same as 1 minus 2 sine squared of that angle. So I'm going to use the second one, and I'm going to write it with a theta instead of an a. So we know that cosine of 2 theta should be 1 minus 2 sine squared theta, just using the second angle that we came up with, right? Now, if you did the rest of your work, if you did all of this and everything correctly, you should get the same answer no matter what, but I encourage you to use the formula that requires the least amount of your worked out answers, just in case you made an error, okay? All right, so let's go ahead and plug this in. So I have 1 minus 2. Now sine theta is squared here. So we're going to square whatever that sine value is. And the sine value was given. It's 8/17. So again, this is where I would use my fraction button to make sure I don't make an error. If I type in 8 and then my fraction button over 17, and then I can use my squaring button, which is my little x squared here. It will give me that that is equal to 1 minus 2 times 64 over 289. Okay, and then again, I can keep doing it on my calculator. Now I need to go ahead and multiply it by 2. So times 2. So I have 1 minus 128 over 289. Okay. So if you want to do this in your calculator, you could go ahead and make this negative and then add 1 to it, but I'm going to go ahead and clear it and show you how to type it in like this. We do 1 minus, and then you don't even have to use parentheses if you're using your fraction button. So you do 128 over 289. And it tells us that our final answer should be 161 over 289. 161 over 289. And it saves you having to get the common denominator and all that stuff. Okay. All right. And then our last problem here is to find the tangent value. Okay. So notice we only have one formula for tangent. My one formula for tangent is that this should equal 2 times tangent theta all over 1 minus tangent squared theta. Right? So using the same formula, just putting in a theta instead of an a, because we're using thetas here. Okay. All right, so we want to be able to plug this in, but notice we got to figure out what our tangent value is, right, of this angle. If you remember, tangent is opposite over adjacent. So for this specific triangle, tangent theta is going to be the opposite, which is 8, over the adjacent, which is negative 15. 8 over negative 15. So that's what I'm going to plug in here for my tangent values. Okay, so that means I have 2 times 8 over negative 15 on top, and on bottom I have 1 minus 8 over negative 15 squared. Okay, and then I can do my simplifying. So on top, when I multiply these two together, again, you can use your calculator. If you're not good with fractions, you can do 2 times. And again, you don't need parentheses if you're using your fraction button. 8 over negative 15. Oh, it doesn't like the negative on the bottom. We'll do negative 8 over 15. Same thing. Which gives me negative 16 over 15. Right? On bottom, I have 1 minus. Now, if I square this on top and bottom, I should get 64 over 225. So I have negative 16 over 15. On bottom, I'm going to go ahead and use my fraction button to calculate this. So 1 minus 64 over 225 gives me 161 over 225. 161. And then I'm going to go ahead and use my calculator to do this division. So negative 16 over 15. Make sure you're using your fraction button. Okay, and then the division for our main fraction here, right? This is where I hit my division bar. 161 fraction button 225. And we end up with negative 240 over 161. Negative 240 over 161. And we can just leave it like that. So I'm going to go ahead and circle my answer. Right. Okay. All right. So now we know how to use our different formulas and how to decide which one is the appropriate formula that best suits our needs. I want to show you another one where we're kind of using the same idea, but in a different way. Okay. So notice on this one, they gave us the double angle and we just had to plug in the values, which wasn't too hard to come up with this triangle because they gave us one of the trig function values, right? They said sine theta equals this value. So we were able to create the triangle off of those values. Okay, let me show you one that's a little bit different. So this one says we want to find the 6 trigonometric functions for theta. So we want sine, cosine, tangent, cosecant, secant, cotangent. So we want to find all of those. But notice what they're giving us here is a double angle value. They're not saying cosine of theta equals 4/5. So we can't take 4 and 5 and create a triangle out of that. They're giving us the double angle value, and we have to figure out how to come up with that. Okay, so the first thing that I notice is that they tell us that our theta is between 90 degrees and 180 degrees. So if I think about that in terms of a quadrant, right, this is 90 degrees and this is 180 degrees. So our angle is somewhere in there, right, my theta value. So I'm going to go ahead and draw my reference triangle in quadrant 2, since I know it's between 90 degrees and 180 degrees. But I can't label the cosine value with 4 and 5 because this is cosine of 2 theta, not cosine theta. So I need to use one of my double angle formulas to see if I can use that to solve for regular theta instead of cosine 2 theta. I just want regular theta. So if I look at my cosine angles here, I have a cosine squared and a sine squared. Well, I don't know anything about the sine value, right? I was only given the cosine of a double angle. So I don't really want to use the ones that have sines in them since all I was given was cosine. So I'm going to use this last one. I'm going to use this last one that says that cosine, and I'm going to use theta instead of a, cosine of 2 theta is equal to 2 cosine squared theta minus 1. So all I did was write this formula there because that's the one I'm going to use. And now I can go ahead and plug in what that cosine of 2 theta value is, right? Because that was given. They told me that cosine of 2 theta equals 4/5. So I can go ahead and replace cosine of 2 theta with 4/5. So this tells me that 4/5 is equal to 2 cosine squared theta minus 1. So I should be able to solve this to get cosine, to get, well, cosine theta or theta completely by itself, right? So I'm going to go ahead and move the 1 to the other side. If I add 1 to both sides, okay, again, I can use my fraction button, or I could write this 1 as 5 over 5. 5 over 5 plus 4 over 5 gives me 9 over 5, which is equal to 2 cosine squared theta. Now, I want to get the cosine theta by itself, so I need to get rid of this 2. So the way I can get rid of this 2 is by multiplying by the reciprocal, right, or dividing off 2. So if I multiply this side by 1/2, that 2 will go away, right? But if I multiply that side by 1/2, I have to multiply this side by 1/2. So now I have 9/10 is equal to cosine squared theta. So I'm almost there, right? I want to be able to draw my triangle, but I need it to just be a regular theta, not a squared theta. So I'm going to go ahead and take the square root of both sides. And when I take the square root of both sides, I have to use plus or minus, right? So I get plus or minus the square root of 9/10 is equal to cosine theta, right? So I need to figure out, do I want the positive or the negative, right? I can't have both. So if I am in the second quadrant and I am looking at the cosine value, cosine relates to x. So my x's in quadrant 2 are going to be negative. Okay, so this is the one that I want. I want the negative value. So that means that cosine theta is equal to, now the square root of 9 I can simplify. That's just 3, right? And on bottom, square root of 10 does not simplify, so I'm just going to leave it as the square root of 10. Okay, so I end up with the cosine of theta is equal to negative 3 over root 10. So that gives me one of my trig functions, right? But I also need to come up with the other 5 trig functions. So I'm going to use the fact that cosine is adjacent over hypotenuse to label this triangle. Hypotenuse is always positive. So we know the square root of 10 goes here, and it's going to be positive, which means the negative has to go with the 3 for our adjacent side. Okay. And now that we know the hypotenuse and we know the adjacent side, we should be able to find this opposite y length, right? Just by doing the Pythagorean theorem. So I'm going to go ahead and say for the Pythagorean theorem, we know that x squared, so negative 3 squared, plus our y squared, which we don't know, y squared, is equal to our hypotenuse squared. So square root of 10 squared. And when I simplify, that gives me 9 plus y squared equals 10. I move my 9 to the other side by subtracting. So that means that y squared equals 1. And then when I take the square root of both sides, I get y equals plus or minus the square root of 1, right? Or y equals plus or minus 1, because the square root of 1 is 1. And here we can see that because our y is above our x-axis, it's going to have a positive 1 value. Okay? Positive. All right, so now that we have our triangle completely filled out, now we should be able to identify those 6 trig functions. And I'm just going to kind of write it down the middle here because I ran out of room. So we know that sine of theta, sine is opposite over hypotenuse. So opposite over hypotenuse is going to be 1 over the square root of 10. And then this book is going to have us rationalize the denominator. So if I multiply by the square root of 10 over the square root of 10, that's going to give me the square root of 10 over 10 for my sine value, right? All right, and then I'm going to go ahead and do the inverse of sine, which is our cosecant theta. And I'm going to go ahead and just flip it before I rationalize the denominator. Cosecant we know is hypotenuse over opposite, or in other words, the square root of 10 over 1, which is just the square root of 10. Okay. Then we need cosine theta, which we got over here, right? Cosine theta we know is negative 3 over square root of 10. And then we need to rationalize the denominator. So if I multiply on top and bottom by the square root of 10, which I'm not going to do because I don't have enough room in here, I end up with negative 3 square root of 10 over 10. Okay. And then I'm going to do the inverse of cosine, which is secant. Secant theta is what I get when I invert my cosine function value, and I'm going to do it before I rationalized. So that gives me square root of 10 over 3, and it's negative. Okay, and then the last value that I need to do is tangent theta and cotangent theta. So tangent is opposite over adjacent. So opposite is 1 over adjacent, which is negative 3. So 1 over negative 3 is negative 1/3, right? And then cotangent is just the inverse of that. So if I take 1 over negative 3 and flip it, I get negative 3. Okay? All right. So there's our 6 trig function values. So the only difference between this one and the last one that we did is that we couldn't just go straight to our triangle from the value that was given, right? Because our triangle has to be made from our regular theta values, not 2 theta. We can't create a triangle for 2 theta. So we use one of our formulas, plug in our value that was given so that we can solve it for a regular cosine theta value or sine theta value or something that we can use to make our triangle. Okay? All right. I want to show you one more verify function, and then I want to show you two examples of how you can use these formulas, these double angle formulas, backwards, where instead of you being given the right hand side and you fill in the left, you're going to be given the left and you have to figure out what the right side was to simplify. Okay, so here is an example of a proof that I might give you on your homework or on a test. Excuse me, to prove that cosine to the 4th beta minus sine to the 4th beta equals cosine 2 beta. So what I notice about this left-hand side is that these are perfect square terms. And if we have a difference of perfect squared terms, I know that I can factor that as a difference of squares. So I'm going to go ahead and start with the left-hand side, which is cosine to the 4th beta minus sine to the 4th beta. And I'm going to go ahead and factor that as a difference of squares, right? So my base here that's being squared, in order to get a 4th power, would have to be a squared power, right? So this would factor into cosine squared beta plus sine squared beta times cosine squared beta minus sine squared beta. Are y'all with me? Just factoring this into a perfect difference of squares. And now this is one of our Pythagorean identities. Okay, right? Cosine squared plus sine squared is what? Or you could write it in the opposite order. Sine squared plus cosine squared. You sin, you confess, you're one with God, right? So this addition, this all just equals 1, right? And then cosine squared beta and sine squared beta, that's one of the identities that we just came up with, right? If I bring my little page here where I have them all written, that was the very first formula that we got for cosine of 2a. So if we have cosine squared of the angle minus sine squared of the angle, that's the same thing as cosine of 2 times that angle. So here we can replace this, right? This whole thing is a double angle identity for cosine. So this whole thing just becomes cosine of 2 times the angle, and our angle here is beta. So this just becomes cosine of 2 beta, right? And then if I multiply these together, 1 times cosine 2 beta is just cosine of 2 beta. Okay, and that's exactly what we were trying to prove here. Okay? So we're done. So that's kind of what a proof looks like. All we had to do was 2 steps really, right? We had to factor this, and then each of the factored quantities, this one became 1 because it was a Pythagorean identity, and this side was one of our double angle identities. So when you're working out proofs like this, this is what I'm looking for, the rationalization of how you did what you did. Saying this is a Pythagorean identity, which gives you 1, saying this is a double angle identity, gives you cosine 2 beta. That lets me know, okay, they know how to replace those things. Okay? All right. Let's look at this one. It says simplify each expression. Now, they're not giving us, if you look at the angles that are the formulas that we came up with, they're not giving us cosine of some angle, sine of some angle, tangent of some angle, right? They're giving us an expression. So we have to look at this expression and see if it looks vaguely familiar in regards to any of these formulas we came up with, right? So this looks like 2 times cosine of some angle minus 1. So if I look at these, this is not 2 times cosine of some angle minus 1. This one doesn't even have cosine, but it does look very similar to this one, right? This looks like 2 times cosine squared of an angle equals 1. So this is the formula I'm going to try to relate it to. So I'm going to just go ahead and write that formula out to the side here. I'm just going to say recall cosine of 2a is equal to 2 times cosine squared a minus 1. Okay, so what we were given over here is kind of like what looks like the right-hand side of this formula, right? The only difference between what they gave us and what's written here is we have an a and they have a 5x. So if a is 5x, then we should be able to figure out what this side is, right? Because this is just 2 times whatever a is. So if we're saying that a is 5x, then 2 times 5x would give me 10x, right? So what we have written over here is the same as cosine of 10x. And that's all we had to do. We just wanted to rewrite this. This is cosine of 10x. Okay. So does that make sense? We're taking the formula, whatever side we're given, we're trying to figure out the opposite formula. In this case, we could see that the angle inside here was 5x. So that means that our double angle on the other side would be 2 times that 5x, which gives us 10x. And then this is something we can't go any further with that, right? Because we don't know what x is. All right, let's do the same thing with this one. Let's see if this looks like any of the formulas that we've dealt with. So I'm going to bring my formula page back over here. This looks like sine of an angle times cosine of an angle. And these are the same angles. So we're looking for a formula that has sine times cosine of the same angle. Well, these are not multiplied. This only has sine, this only has cosine. This one has sine of the same angle times cosine of the same angle, but it has a 2. But that's okay, because this maybe we can work with, because it looks very similar. So I'm going to go ahead and write that formula right here. Recall that sine of 2a is equal to 2 times sine a cosine a. All right. So I'm going to go ahead and just rewrite this as if this is what we were given. Okay, so we can see here that the angle that's the same on my sine and my cosine here has to be 165, right? So the A here and the A here has to be 165 degrees. So I just want to rewrite this whole formula with that 165 degrees. So if A is 165, then inside here we have 2 times 165 degrees, right? So I'm just going to rewrite the formula, putting in that angle value. So that means we have sine of 2 times 165 degrees is 330 degrees. So 330 degrees is equal to 2 times sine 165 degrees cosine 165 degrees. Okay. Now, I can't on this one, like the last one, go ahead and say, oh, well, this just equals sine of 330, right? Because what we were given does not yet look like this right-hand side, right? These two are not the same, so I can't just replace it. The thing that I have that is stopping my right-hand side from looking like what I was given here is this 2, right? I wasn't given a 2. So I want to go ahead and I need to get rid of the 2. And the way that I can get rid of the 2, if it's written side by side, it's being multiplied, right? So to undo that multiplication, I can just divide it off. So I'm just going to divide 2 off of each side, or you can think of that as multiplying both sides by a half, right? Multiply this side by a half, multiply this side by a half. That way my 2's cancel, right? So I end up with 1/2 times the sine of 330 degrees is equal to sine of 165 cosine of 165. Okay, so now my right-hand side looks exactly like what I was given. So I know that what I was given has to be equal to 1/2 sine of 330, right? So now I just need to figure out what 1/2 sine of 330 is. I know that this is equal to 1/2 sine of 330 degrees. 330 degrees is an angle value that I should be able to find on my chart, right? On this chart from section 5.3. You can either use the graph or you could use the unit angle. But if I look up 330 degrees and I go over to find the sine value, I can see that it should be -1/2. So sine of 330 degrees is -1/2, and then I'm taking half of that. So 1/2 times -1/2 gives me -1/4. Okay. So can you see how on these problems we started with the right-hand side of the formula in order to simplify the left-hand side of the formula? Okay, so we should be able to use these double angle formulas going both directions, right? All right, I do have one more proof on the last page. I was thinking I was not going to go over it, but I know that there's some proofs in your homework. So I think the more examples that you can have of how to do these proofs, the better. So we're going to go ahead and do this one. I'm sorry that this video is going to be a little bit longer, but better to have seen it, and hopefully it will help you on some of your homework problems. So what this one says is that we want to write cosine of 3x in terms of just cosine x. So what we're saying here, if you look at our formulas, is it's like we're trying to come up with a new formula. These were all cosine of 2a, cosine 2a, cosine 2a. And remember when we started finding a formula for cosine of 2a, or we started finding the formula for sine of 2a, or we started finding the formula for tangent of 2a, what we did is we wrote that 2a as a plus a in order to come up with these formulas, right? Well, what they're wanting us to do is they're wanting us to come up with a formula of cosine of 3a. And when they say it's in terms of cosine, that means whatever we end up with over here on the right-hand side should only have cosines in it. We shouldn't have any sines, we shouldn't have any tangents or anything like that, okay? So let's see if we can come up with a formula, a triple angle formula here that only has cosine. So we're going to go ahead and start with cosine of 3a. And I'm going to go ahead and rewrite this in something that I can use, right? 3x, sorry. Pretend that's an x. 3x, okay? So I could write this out as x plus x plus x, right? I could say this is the same thing as cosine of x plus x plus x. But I don't really need to be adding three things, right? Because I have a formula for cosine. I'm going to put it over here. Recall. I have a cosine of a plus b formula that I can use, right? My cosine of a plus b was my CAB-SAB formula, which says that I do cosine of a cosine of b minus sine a sine b. Right? All right, so I can use this formula if I'm just adding two things. So instead of writing it out as three different x's, I really just need an addition of two things. So I'm just going to go ahead and group these first two x's together. And I'm just going to rewrite this as cosine of 2x plus x. Right? Because I really only need to be adding two things in order to use this formula. 3 is just a little bit redundant. So I'm going to break up 3x and write it as 2x plus x. That way this is my first angle and this is my second angle, and I can plug it into this cosine, my CAB-SAB formula, right? Which says to do cosine of my first angle times cosine of my second angle. So that's going to give me cosine 2x times cosine x, and then I subtract sine of my first angle, so sine 2x times sine of my second angle, so sine x. Okay, all right, so now I've done a little bit of simplifying, right? Now I have this, but remember, we didn't want to end up with sines. We really just want cosines because we want it in terms of cosine. So let's see what else I can replace. So what I noticed right away is that here I have a double angle formula, and I could use a double angle formula here, right? So double angle formula, double angle formula, okay, on both of those. So if I look at my page that has all my double angles formulas on there, I don't have a choice for the sine one. I have to use this one, right? But for my cosine one, I could choose to use one that specifically has cosine values. So I'm going to use this one for my cosine. So I'm going to write over here, recall. These are the two angles that I'm going to use. I'm going to use this third one that says that cosine of 2a is the same as 2 times cosine squared a minus 1. And then my sine of a double angle formula. So sine 2a is equal to 2 sine a cosine a. Okay? So I have my two formulas written down. So I'm just going to replace these two pieces. So cosine of 2x, right? So I'm going to be using x's when I plug this in. This piece is going to become 2 cosine squared x minus 1 times cosine x. Okay, so notice all I did is replace that double angle with its formula minus, I want to do the same thing on this one, right? So I'm going to go ahead and put in the double angle for that one, which is 2 sine x cosine x, right? Because we have x's, not a's here, times sine x. Okay, so now what? We only want cosines. So I'm going to go ahead and just distribute this cosine x into these two terms. Do I want to do that? Do I need to do that? Yeah, why not? So if I do cosine squared x times another cosine x, I could write that as cosine to the third x, but I'm actually just going to write it side by side for a second. I'm going to go ahead and just say cosine squared x times the cosine x I'm multiplying in, minus 1 times cosine x is cosine x. And then this negative I don't have to distribute because this is all just one term. Minus 2 sine x. This is a sine squared x now, right? Because I have sine squared, sine x, so sine squared x, cosine x. Where can I go from here? Oh, I see something. I'm going to write this term and this term side by side. Because if I write these two together, I see that this one has a cosine squared x and I see that this one has a sine squared x, right? And they have a 2 in common and they have a cosine x in common. So I'm going to go ahead and just write those side by side for a second. So 2 cosine x, or cosine squared x times cosine x minus 2 sine squared x cosine x, and then I have this other term which is a minus cosine x. Okay, so what I'm noticing is that I could take a 2 and a cosine x out of both of those terms. No, not this one, just the first two. So if I take a 2 cosine x out of those first two terms, this term is going to be left with cosine squared x, and this term is going to be left with minus sine squared x, right? Minus cosine x. And now what we're left with in here is actually a double identity, right? Double angle formula. If I look at my cheat sheet here, right? Cosine squared of an angle minus sine squared of an angle is the cosine of 2a. So I'm going to go ahead and put that in. So this whole piece becomes cosine 2x. So I have 2 cosine x times cosine 2x minus cosine x. So even though I was able to substitute in a double angle that got rid of the sign, but it didn't get rid of this 2 here, right? So if I look back up at my instructions, it wants everything in terms of cosine x, right? So I need to rewrite this where it does have a cosine here, but I want it with cosine of just x, not cosine of 2x, right? So I'm going to look for my double angles again. Even though I just replaced to get rid of this one with cosine of 2x, now I can replace that cosine of 2x with one that just has cosines, right? So I can use a different double angle formula to put in there, right? Which is actually the one I have written up here, which says that cosine of 2x should be 2 cosine squared x minus 1. Double angle formula. So this is going to give me 2 cosine squared x minus 1, and then I have a 2 cosine x here. Okay, so let's just simplify this as much as we can. If I distribute this in here, then I end up with 2 cosine x times 2 cosine squared x, which is going to be 4 cosine cubed x, right? Because I have a cosine x times a cosine squared x. And then I'm going to distribute 2 cosine x times negative 1, which is negative 2 cosine x minus cosine x. And then I have these like terms right here. So these like terms I can combine. So this gives me 4 cosine cubed x minus 3 cosine x. And now I have my formula, because I forgot all my equal signs. I have my original triple angle formula, right, written in terms of just cosine x. So we can write this as 4 cosine cubed x minus 3 cosine x. And we are done. Okay? All right, so that is the end of section 5.5. You should now be able to complete the homework assignment corresponding to that. If you have questions, let me know. Otherwise, I'll see you on the next video.